So myself, Dr. Cr3, Kesavulu, Associate Professor, Department of Physics, Institute of Aeronautical Engineering, Dundigal, Hyderabad. Today I am going to discuss about the optical and nonlinear properties in chromium 3 plus dope YAG crystal. YAG is nothing but yttrium aluminum garnet crystal. This is one of the important topic from the laser glass spectroscopy. So last session and the previous session was discussed on the energy transfer from gadolinium 3 plus to terbium 3 plus ion silico-porous glasses for green laser application. In that, we are going to discuss about the introduction, experimental methods, techniques, results and discussion, and conclusion. These are the we are discussed on the energy transfer from gadolinium 3 plus ion, terbium 3 plus ions in silico-porous glasses. So today we are going to discuss about the optical and nonlinear properties in chromium 3 plus dope YAG crystal. In that, we are going to discuss about the introduction, theoretical basis, jet scan technique, optical properties, and finally with conclusion. These are the we are going to discuss about the today talk, that is mainly involved on the optical and nonlinear properties in chromium 3 plus dope YAG crystal. So first introduction. In the introduction, we are going to study about the nonlinear properties in particularly important in laser active media because standing wave in the laser cavity produce light induced grating that cause hole burning, self-focusing, temporal and spatial self-phase modulation effects. In fact, the first experimental demonstration of the spatial hole burning effect was made on the ruby crystal. Ruby is nothing but chromium 3 plus doped aluminum oxide, that is called ruby. This we are going to discuss about the refractive index change in active media that we are going to study in the chromium 3 plus doped YAG crystal. So chromium 3 plus doped crystals are convenient material because of the WT metastable state can be populated easily in the continuous wave region due to its long luminescence lifetime. So usually chromium 3 plus ions in metastable state having the longer luminescence lifetime, that is in the order of milliseconds. So in this paper we intend to further address the physical origin of delta alpha p, that is polarizability difference in the chromium 3 plus doped crystals. For the purpose, the time resolved jet scan measurements was performed in the chromium 3 plus doped YAG crystal using argon 3 plus argon ion is as a pumping source, that is a lambda usual 457 nanometer. So that is we are going to pumping the argon ion laser. So what is the introduction main application of the jet scan technique? The nonlinear optics jet scan technique is used to measure the nonlinear refractive index change, that is N2. Usually N1 is the linear refractive index and N2 is the nonlinear refractive, that is Kerr nonlinearity, that we are going to study in the by using the jet scan technique. And also we can study the nonlinear absorption coefficient delta alpha via the closed and open methods we are going to study. This can be extremely used since it gives the focal spot size of the beam of diffraction limited optics independent of the irradiation for small nonlinearities. In principle, the jet scan can be used to measure very small spot size using a thin samples. So thin samples means the thickness of the sample should be very less than Z naught. Z naught is the diffraction length that should be less than would be sample thickness. That is a focal beam. That is in Z naught is how you are calculating Z naught is pi omega naught square by lambda. Here omega naught is the focal beam width. That is a focal beam width that we are going to calculate by using the wavelength. Which wavelength we are going to exciting the by using jet scan technique. So here argon ion laser, that is a lambda into 457 nanometer we are using. By using that one, we are calculating the diffractive length Z naught. So thickness sample of thickness should be less than to Z naught. Then only we can going to study the nonlinearity refractive index. So what is the important applications in the we can use for the jet scan technique in the telecommunication applications and optical switching, sensor production, optical information storage, and optical computing. These are the important applications involved in the by using the jet scan technique. Now we are going to study the theoretical basis. In order to obtain the refractive index change, that is RIC means refractive index change produced by the excited state population, the refractive index can be written as N equal to N naught plus delta N. This N naught is the linear refractive index and delta N is the difference between the linearity and non-linearity refractive index, where the refractive index of the unpumped crystal is given by formula is n naught square is equal 1 plus 4 pi FL sigma m plus nt is psi g. That is psi g is the ground state and metastable state. That is FL equal to n naught square plus 2 by 3. So this is the Lorentz focal field. That is, we can say the Lorentz focal field is FL. This is Lorentz focal field. Sigma m, that is psi m, is represents the host matrix susceptibility, and nt is the total chromium 3 plus ions concentration for ground state, and that is psi g means that is, so this is the complex susceptibility. So that is the chromium 3 plus ions in the ground state and excited state of the nonlinearly refractive index. So the refractive index change is proportional to the susceptibility change due to the excited state population and is given by, so delta n equal 2 pi by n naught FL square. So excited state concentration and nt, that is ground state, this one. So sigma exe and sigma g is the ground state and excited state of the susceptibility, where delta n is the complex quantity which real part is proportional to the polarizability difference. The polarizability difference experienced by the chromium 3 plus ions when they are brought into their excited state. So the polarizability difference delta alpha p is equal to real number Re equal to psi ex minus psi g by nt. That is the susceptibility chi, that is ex minus is excited state to ground state by concentration, total concentration of the chromium 3 plus S. By using this formula, we can calculate the delta n. That is a complex quantity value we can calculate by using this formula. So next, the imaginary part is proportional to the delta sigma is the sigma ex minus sigma g, that is excited state to ground state. The difference of the ion ground and excited state absorption cross sections. So sigma ex and sigma g is the excited state absorption cross section and ground state absorption cross section. We are going to calculate the delta sigma. So we shall first consider the unsaturated pump region, for the which is the concentration of the excited state concentration and a total concentration of chromium 3 plus ions, and the intensity I and Is is saturation intensity. Approximation is valid for the n, that means the total concentration. It should be more than the excited state concentration. So with the pump saturation intensity given by the, so this is formula, we can calculate the saturation intensity of the focused beam laser. That is h mu divided by sigma g and tau naught. Tau naught is the lifetime of the chromium 3 plus ion. Sigma g is the ground state of the absorption cross section. So where tau naught is the excited state lifetime, therefore delta n is proportional to the pump intensity. So it can be written similarly to the Kerr nonlinear effect. So similarly, we can say that is the Kerr nonlinear effect. That means we are going to study the nonlinear properties. In that, we can study the n equal to n naught plus n2i. So n2 is the nonlinear refractive index, I is the intensity of the focused beam. With n2 is given by the reference number 1, we can calculate the n2 value. That is nonlinear refractive index n2 is nt by is, that is total concentration of chromium 3 plus ions and saturation intensity of the focal length. That's a 2 pi by n naught and linear refractive index. Fl is the, that is length of the focal beam. Delta alpha is the polarizability difference, lambda by 4 pi into delta sigma, that is absorption, excited state absorption coefficient. These are, we are going to find out the n2 value. By using this formula, we are calculating the n2 value. So n2 is the complex quantity which can be written as n2 equal n2 dash minus I n2 double dash. That is a real part, and the other one is imaginary part. So real part and imaginary part we are going to calculate the by using the n2 equal n1 dash minus I n2 double dash. n1 n2 dash is the real part, n2 double dash is the imaginary part. That is proportional to the delta alpha p, which is mostly positive in order to ion doped materials. The imaginary part, the n2 double dash is the imaginary part. This is positive in the case of strong excited state absorption, ESA, that means excited state absorption, so that delta sigma is greater than 0. So by using above formula, we can calculate the NT value. At the same time, we can calculate the polarizability difference of the nonlinear refractive index we can calculate by using. So what is the next one is jet scan. So how you are going to measure the jet scan by using the jet scan technique. So jet scan technique is simple technique and popular experimental technique used to measure the intensity dependent nonlinear susceptibility of the material. Hallmark's jet scan system, that is a Hallmark company is provided the jet scan system, is the simple implementation of jet scan technique that can be used to characterize the optical materials. We can characterize the optical materials by using the Hallmark's jet scan technique. This is a jet scan method. We are focusing the laser. In this laser place, we can use the argon ion laser. In between this lens sample we are keeping here. In the after that we can photo detector. The photo detector will detect the sample and transmitted signal that will be sent to the data acquisition part. Then in CPU we can save the data by using the we are collecting the jet scan data. To how jet scan technique works by using the jet scan technique. This is the simple and unique technique to study the nonlinear properties. See here sample we are focusing here. So laser will be focused on the sample. So the focal beam should be very important. The sample should be thickness should be less than to z naught. That means diffracted length should be diffraction length z naught. That is a focal beam length should be less than to the thickness of the sample. So here the thin sample we are focusing here. Then after transmitted light will be detecting the photo detector. Then after photo detector we are going this sample we are varying minus z, that is length, that is we are intensity versus transmittance versus distance should be minus z to plus z. Here is this center point. See here that is z naught value we are focusing here. We are imaging minus z to plus z. Here we are scanning the data from thin sample data. We are focusing the minus z to plus z. That is a distance between the z value versus we are transmittance intensity we are focusing. By using that transmittance absorbance, that signal only we are collecting, and we are and draw the jet scan wave, open aperture and the as well as closed aperture. This is the experimental setup for the jet scan technique. The sample travels along the focal axis of the laser beam. The photo detector collects the signal of transmitted signal, how much transmitted by the signal we are collecting by the photo detector. That signal should be transferred to the data acquisition. That is a photo multiplier to that too we are connecting to the CPU. So PC you are the collecting the all the data. This is the jet scan technique, how jet scan works by using the samples. So the jet scan technique, Hamadi technique used to characterize the complex susceptibility of the given material. The jet scan technique is the most popular one due to its sensitivity and also due to its simplicity compared to the other techniques. So the technique relies on the basic idea of relating the far field beam center intensity variation to the index variation. This can be done by the monitoring the transmitter's variation of the pumped sample as a function of the sample position along the incident beam. So we are in this one sample position here we are varying it. That is a distance varying from minus z to plus z. Here focusing the sample. So how much position will be varying from minus z to z plus z. That transmitters light we are observing photo detector we are detecting. After that it will transfer to the data acquisition and we are saving the data in the CPU. So that way you are collecting the data by using the function of the sample position along the incident beam. So that way we are measuring the jet scan measurements. This transmittance presents peak and valley, and the variation between this peak and valley is proportional to the induced phase shift through the normalized transmittance. Delta TPV is given by the reference number 6. By using this formula, delta TPV is similar to 0. Approximately equal to 0.406 1 minus s whole power of 0.25 delta pi naught by 1 plus I naught by is whole power of 0.52. By using this one, that is a value we are getting just can peak like that. So that we are calculating the how that peaks will be value and peak value. How should be varying that here. So this we are in this one, this peak intensity, this value how much down, how much intensity is there. That we are going to study By using this formula, you can calculate the where delta pi naught is the K L effective N2 is on axis phase shift, K equal to 2 pi by lambda is the wave vector, L effective is the effective sample length, that is effective sample, that is how you are calculating 1 minus exponential of minus alpha a. Alpha a is the linear absorption coefficient, I naught is the on axis intensity at focus, Is is the saturation intensity, and capital S is the transmittance aperture factor, that is aperture factor, how much this is open aperture and closed aperture, that we are calculating by the S value. S is 0.5 means that is uh, open aperture. Full aperture means that completely one means completely we are focusing in the. So just can take the measurements were performed by choosing the chopping the argon plus ion laser at the frequency of F equal 665 Hz, and the closing and the collecting the data at the initial and final time. Your TI is the initial time is 25 milliseconds, the final time is 7.5 milliseconds respectively. In the time resolved jet scan method, we are study the this is jet scan measurement non-linear transmission. Here x-axis position, that is jet position from minus jet to plus jet, and y-axis normalized transmitters, how transmitter signal will be looks like. Here S1 is completely open aperture, that means completely open, slit will be completely open, that means 100% open means we are collecting all the data to the detector. But S2 is 30%, that is a closed circuit, that means where 30% is open, remaining 70% will be closed, that is S2 by S1 we are theoretically we are calculating the by using the theoretical fit. So by using this above equation, we are fitting this equation, we are getting the theoretical fit, and we are calculating the S2 by S1. So by using that theoretical fit, we are calculating the Z naught value here 0.41. That is the diffracted length of the our chromium 3 plus sample will be Z naught is the 0.41 centimeter, and the real and imaginary parts of the non-linear refractive index by using the formula we are calculating the N2 dash, that is real part. N2 dash is the real part of the nonlinear refractive index is 2.2 into 10 power of minus 8, and imaginary part of nonlinear refractive index N2 value is 2.8 in 10 power of minus 8 centimeter square by watt. This we are getting the N1 dash and N2 double. There is a real and imaginary part of the non-linear refractive index. So N1 dash and N2 dash we are getting by using the above equation. By using this fit, we are calculating this value. This the value of delta alpha p, that is polarizability difference. Also we are calculating by using the jet scan technique. That value we are found out that 2.2 into 10 power of minus 25 centimeter cube, and the absorption cross section value. The difference of absorption cross section value of the excited state is the 8.4 into 10 power of minus 21 centimeter square. When we are then calculated from the equation 3. So using the above equation, we are calculating the N1 dash, that is the real part of non-refractive index, N2 double dash, imaginary part of non-refractive index, and also delta alpha p, that is the polarizability difference, and delta sigma. So these parameters we are calculating the from using the jet scan technique. So this is the jet scan measurement profile, that is in the x-axis position, that is the distance from minus z to plus z. This is position focusing the jet scan. This y-axis is normalized transmittance. So by using this jet scan technique, we are calculating the non-linear refractive index, imaginary part and the real part, and also polarizability refractive index, and also absorption coefficient of the delta sigma, absorption cross section. So next jet scan technique. This figure shows the transient jet scan curve measured for the chromium doped YAG crystal. Jet scan peak position is power here using the power equal 5 milliwatt. Excited wavelength is pumping wavelength is 457 nanometer. By using the open circle data fit equation, full curve resulting in the tau. This 1 point we are getting the lifetime of the excited state, lifetime of the chromium 3 plus ions, we are getting the t equal to 1.73 milliseconds. By using this fit, we are calculating the t value, and also by using this fitting only, we can calculate the saturation intensity also. That is Is equal to h mu by sigma g minus tau naught. Tau naught is the 1.73 millisecond. So ground state absorption cross section, and h value Planck constant, mu is the frequency of the chromium 3 plus ions. So by using this fit, we are calculating the saturation intensity of the chromium 3 plus doped YAG crystal found that the 8.3 kilowatt per centimeters square, that is the saturation intensity of the chromium 3 plus ions by using the jet scan technique. Next, coming to the plot for the transmittance variation of the measured at the peak of the jet scan transmittance curve versus on-axis incident laser intensity. So, laser intensity I naught versus we are calculating the delta TP, that is the transmittance variation of the different positions. So, how intensity will be varying from the different positions that we are calculating. By using that calculation, we are fitting the N2 value or real part of the nonlinear refractive index. We are getting the 2.3 into 10 power minus 8 centimeter square per watt. This is by using this graph delta TP versus I naught intensity variation of the transmitters of the each and every peak position, how varying the from minus Z to plus Z. At that time, how intensity is varying. By using that intensity variation, we are calculating the real part of the nonlinear refractive index. That value is by using this fit, we are found that real part of the nonlinear refractive index is 2.3 into 10 power minus 8 centimeter square per watt. So this, by using this graph, we are calculating the nonlinearity refractive index, that is real part, that is 2.3 into 10 power of minus 8 centimeter square per watt. Next, coming to the optical properties. So previously we have discussed the nonlinear properties, that is the nonlinear refractive index N1 and nonlinear refractive index N2 and delta alpha P and sigma G. These are we are calculating the. Now we are going to calculate the optical properties by using the chromium 3 plus absorption. This is optical absorption spectra of the chromium 3 plus of YAG crystal at room temperature. We are observing the wavelength versus absorption coefficient. So here observing the 1, 2, 3, 4, 5 absorption peaks from the ground state quarter A doublet F2 different excited states. So this is the YAG chromium doped YAG crystal. That thickness of the sample is 0.164 centimeter. This is the thickness of the chromium sample. The optical absorption spectra observed at room temperature for chromium 3 plus dope YAG crystal shown in figure. This spectrum exhibit two broad bands peaks around at 430 nanometer. That is energy is 23,256 centimeters and 600 nanometer, that is energy is 16,667 centimeters, along with a solder around 330 nanometer, that is 30,330 centimeters. A small peak at about 670 nanometer here, around 670 nanometer, that is 14,920 centimeters, and a sharp peak one about 688 nanometer, that is 14,535 centimeters. The observed bands are characteristics of the chromium 3 plus ions in octahedral near octahedral symmetry. That is shows the octahedral symmetry. The two broad bands peaks around at 600 nanometer and 430 nanometers is assigned to the spin allowed transition. These two transitions are the spin allowed transition. That is port T2F and port T1F. These are the spin allowed transitions from the ground state to different excited states. Next, by using this optical absorption data only, we can calculate the crystal field parameters, that is the DQ, crystal field parameter DQ and the Raka parameter B, and reduced crystal field DQ by B. We are calculating by using the optical absorption spectra, and energy difference delta E also we have calculated by using this data. But we are calculating the crystal field parameter and the Raka parameter B. We are using the Tanabe-Sugano diagram. By using Tanabe-Sugano diagram, we are calculating the crystal field parameter DQ is evaluated by using the absorption position of the ground state to exit state of the quarter T2G. By using this formula, we are calculating the crystal field parameter DQ value. Next, by using the Raka interelectronic repulsion parameter B value we are calculated by using the dq by into 15 minus x minus 8 by x square minus 10x. By using this, x is the E1 minus E2, that is the energy level excited state to ground state level. That by using this energy levels, we are calculating the x. By substituting this formula, we are calculating the B value, that is the Raka interelectronic repulsion parameter. Also, we are calculating by using this formula. So, in this formula, we are calculating dq, and dq we are substituting here, and at the same time, x value also we are calculating by E1 minus E2 by dq. That value we are substituting in this formula, and finally we are getting B value. That is B is the Raka interelectronic repulsion parameter. And also by using that one, we are calculating the dq by B. That is a reduced crystal field parameter. Also we are calculating by using the optical absorption spectra. Next, coming to the polarization difference delta alpha p versus energy difference delta E of different chromium 3 plus doped oxide crystals. We are comparing our crystal is YAG. This is our present study is yttrium, aluminum, garnet. We are comparing with other crystals. Ruby crystal, that is a chromium doped aluminum oxide. Next, gadolinium doped aluminum oxide. Next, GG garnet and the GSGC. These are the different kind of garnets. And alexandrite, this is also one kind of garnet crystals. So from the figure, they plotted delta alpha p versus energy difference delta E, which is related to the reduced crystal field parameter dq by b. So in the delta alpha E, P is the larger for the low field material like chromium CSGC. So CSGC is having high value and reducing GG and alexandrite and YAG and ruby golden oxide. So YAG is, we are showing that in between to the GG and the ruby. So this is the consequently the polarizability should also be a significant role on the delta alpha P, which is associated to the promotion of the chromium 3 plus ion in the excited state. So by using this graph, we are calculating the how varying the polarizability difference delta alpha versus energy difference of the delta E that we are calculating by using this graph. Next, coming to the finally, we are conclusions. The time reserved scan measurements were performed in the chromium 3 plus dope YAG crystal by using argon ion laser lambda equal 457 nanometer and also 488 nanometer respectively. Thermal effects gives the negligible contribution to the nonlinear refractive index. Measure the all the measurements. Yes, the imaginary part of the determined population induced nonlinear refractive index N2 indicates that the excited state absorption occurs and the chromium doped YAG behaves as a saturable absorber with a saturation intensity of 8.3 kilowatt per centimeter square. By using that formula, you are calculating the saturation intensity also, and also it is useful for the saturable absorbers. Next, the polarizability difference value found to be chromium doped YAG crystal delta alpha p, that is the polarizability difference delta alpha p is 2.2 into 10 power minus 25 centimeter cube is comparable to that obtained in ruby and argent. This is very near to the this value delta alpha p is very near to the obtained sample of the previous studies ruby and argentite crystals. So next, hence the observed delta alpha p decreases with the magnitude of the local crystal field, which is related both the reduced crystal field parameter dqb and the energy difference delta E. These are the we have studied by using the scan technique and also optical absorption spectra. We have studied the optical properties and as well as non-linearity properties in the chromium 3 plus group YAG crystal. See, YAG, this is one of the important yttrium aluminum garnet. This is compared to ruby crystal, this is YAG crystal also one of the important crystal to study the jet scan technique. And jet scan technique, we have studied mainly non-linearity property, that is in linear properties, we are getting linear refractive index n value only. But in the nonlinear study, we are studying the nonlinear refractive index in a real part as well as imaginary part. N2 dash and the N2 double dash. We are getting real part and imaginary part of the refractive index. At the same time, you are getting the polarizability difference of the delta alpha p and also delta sigma also we are calculating the difference of the absorption cross section difference also we are calculating the exact state of the chromium 3%. This all the parameters we are studying in the nonlinear properties by using the jet scan technique. So these are the conclusion of the present study. So these are the references cited in the present work. So this completed work is published in this paper, that is a optical materials is published in the year 2018. So in this study we have studied the completely optical and non-linear properties of the chromium 3 plus doped YAG crystals. And Tanabe-Sugano diagram, this is by using Tanabe-Sugano diagram, we have calculated the crystal field parameter dq and Raka inter-electronic repulsion parameter b value also calculated by using Tanabe-Sugano diagram. These are the important references focused in the present study. So thank you. Next class will be continuing in the next session. Once again, thank you.
Like, share and subscribe. Hit the bell icon for more updates.